Here's our last video. It's a twofer. There's going to be two derivations in this video. Here we're finding the electric field first outside a uniform sphere of charge, which is drawn below. Sphere is already drawn. Done. Draw the electric field outside. Well, outside it's going to be pointing away from it, like so. Done. Next, we need to draw a Gaussian surface outside of that charge, which is going to be out to here. And I want to make a distinction between these two spheres. There's the blue sphere here. That blue sphere is my Gaussian surface, and that goes out to radius little r. There's the sphere of charge. That goes out to the black edge, and that has radius capital R. Same convention as the previous ones. Lowercase for the variable, uppercase for the actual object. Now I got some little nuances. Here I accidentally drew it a little close and this side a little far. I meant for these to be concentric. Concentric means same center. So that's just eyeballing the drawing instead of using a program that gives you nice perfect spheres. Not a big issue. It still should be enough to get the point across, and that's what I really want from you guys. Okay, so I've drawn an okay but not perfect Gaussian surface. What is the area of that Gaussian surface? The area is going out to little r, and we had this in the previous video. Area of a Gaussian surface that is a sphere is 4 pi little r squared. Done. Q enclosed. Well, this is our first uniform volume of charge, which means we're dealing with a charge per unit volume represented by rho. So that the Q enclosed will be equal to rho multiplied by the volume. The volume of a sphere is 4/3 pi r cubed. Note how I got the correct r in that situation. Capital R for the volume of the sphere itself. Done. Electric field. Gauss's law. Electric field multiplied by the area of the Gaussian surface is equal to Q enclosed divided by epsilon naught. Electric field times the area of the Gaussian surface is 4 pi lowercase r squared. Q enclosed for the whole thing, that would be rho 4/3 pi capital R cubed over epsilon naught. Now I've seen students get confused here about having the division written the way I wrote it. The way I wrote it, I could have also written it as rho 4/3 pi r cubed divided by permittivity. Those say the same thing. They're exactly the same thing, and I just want to make sure that you saw it as being the same thing. We got some cancellations to do. Cancellations to do include, get a new color in here, I love that purple. 4s cancel, pi's cancel. I feel silly. That's not how you cancel things. One great thing about working in pencil or digital is the ability to undo. I'm going to focus on this right here. All right, 4s, pi's. R's are different. 3 is only on one side, rho, that's it for cancellations. Giving me the electric field is equal to rho r cubed over 3 epsilon naught little r squared. And that is going to be in the r direction, as in outwards. Not bad. Note that this is an over r squared relationship. So if I went through and found out, oh, does that mean it's the same thing as the electric field is equal to kq over r squared, I would actually end up with the exact same thing. Okay, but I'm going to leave that as something for you to do on your own as need be. Okay. Instead, I'm going to go over and look at what is the electric field inside. The electric field inside is a little trickier. Okay. Forgot my checklist. Got to get that checklist. Copy that thing down. That'll work. All right. Already drew the charge. Done. Here's one thing though. I'm going to be doing inside for this one. So here-ish. The electric field pointing away from the center of this whole thing. Now in the shell one, I said it was going to be 0, but this is different because there is charge enclosed, so I can't just jump ahead like I did on the other one. Okay, so I've drawn the electric field. Let's draw that Gaussian surface. Gaussian surface is going to be another sphere. Out to here. And it's going to have radius r. Just like the other video or other part of the video, that whole thing's out to r. Gaussian surface is drawn. Okay. Area of the Gaussian surface, that goes out to little r. Done. Q enclosed. Again, this is a rho is equal to charge per unit volume. So Q enclosed will be equal to rho multiplied by that volume. What volume though? What does enclosed really mean? Enclosed means enclosed by the Gaussian surface. So I don't care about this stuff. I only care about this stuff in here. That's just the stuff that goes out to lowercase r. So it's out to 4/3 pi r cubed. Okay. We don't even use capital R in this one. Next. Q enclosed is determined. It's in 2 colors, but it's determined. Let's find that electric field. Same process as previously. Electric field. Area of the Gaussian surface is 4 pi r squared. Q enclosed is rho 4 pi r cubed divided by 3 epsilon naught, permittivity that is. So I'm writing it that little cleaner way. A little bit of cleanup here. 4 pi r squared. Well, that will reduce this down to just r. Leaving us with electric field is equal to rho r over 3 epsilon naught in the outwards direction. That is the electric field inside of the sphere, the uniform sphere of charge. You get stuff like this with insulators. You do not get this with conductors, because for conductors, all the charge will be at the surface, like the shell sphere. Okay, so this is possible with insulators. And only very briefly with conductors. Because that electric field inside is going to push that excess charge to the surface for a conductor. For an insulator, they're stuck in place. So there we go. Electric field outside, the electric field inside. I'm going to combine those results into a single graph of the electric field versus the distance away. Note that my variable is lowercase r. And this will just be the magnitude of the electric field on the vertical axis. There's going to be a distinction between inside a radius r and outside. Inside, it is a nice linear equation. Outside, it is a 1 over r squared equation. Are they the same value at that location? Let's check that out. This is like so. At r is equal to r. Sounds silly out loud, so it helps a lot to write it out. At lowercase r is equal to capital R, we end up with electric field is equal to rho r cubed over 3 epsilon naught capital R squared. Get some cancellations there, and I get rho capital R over 3 epsilon naught. That looks kind of familiar. Because it's what you get when lowercase r down here is equal to capital R, which is, so yes, these do give the same result at that location. There you go. That is the electric field inside and outside of a uniformly charged sphere.